So it's an honor to be here and to present the speakers of the second session. So first of all, Ana Maria Font, Yukawa, hierarchies and FC regards.
So yes, I'm going to talk about Yukawa hierarchies in F-theory gods, and it's based on work done in collaboration with Luis, Fernando Marchesano, and Diego Regalado, and the three of them are here at the Institute. So the outline of the talk is yesterday, today, and tomorrow, and for me, yesterday is about 25 years ago. This picture is at the time I was getting ready to go to return and start my tenure in Caracas. No, I think there it's distorted. I think it's somehow distorted the screen. No? And but you had more hair, Luis, so you don't complain. Okay. So I was getting ready. Yeah, I was getting ready to go back. We had already written a couple of papers. The collaboration continued, mostly over the Atlantic. But at some point, I came here. I worked at this excellent Instituto de Física Teórica. Definitely thanks to Luis, I could come. So for me, it's a double pleasure to be here to celebrate Luis' 60th birthday. And from the heart, I thank the chicos, Angel, Fernando, and Pablo for organizing the event and inviting me. So you see, I'm the Pichichi in this liga. See, I have as many goals, almost as Messi or Cristiano.
I complain. I have here as Fernando, but also as F.
Yeah.
Put them together and adds up to 31.
Okay. Yes. So because of his character and also playing a little bit with his name, I often think of Luis as a king. Not one that goes on safari, except perhaps to hunt for the Hicks, but rather one like him. He's Alfonso el Sabio, the wise. And he thought he could give some advice to the Lord Almighty himself, some useful hints for the better ordering of the universe. And indeed, Luis has given some useful hints, like maybe supersymmetry, how supersymmetry breaking can trigger electroweak symmetry breaking, or combining supergravity and grand unification, or superstrings, the low energy implications of superstrings, S-duality, of course. I mean, of course, there is a duality, strong coupling duality in strong weak coupling duality strings. A complete theory of soft terms after supersymmetry breaking in string theory using clever and useful parameters. Look, you can also get the standard model from intersecting branes. And of course, everything is in the book. And by the way, the cover illustration here represents some intersecting brane model. It was designed by Luis' son, Jorge, if I understand. And it represents intersecting brane model of a class belonging to a class of Madrid models. Like this here, you have three branes. Oops. But you have three branes here, three branes here. So I had a vague recollection that I had seen another Madrid model. And indeed, Carmen confirmed this memory with this picture. And this is what I call a top Madrid model. Yeah. And you see also that the attachment of Luis to strings goes a long way back. And I don't know, this was perhaps around 75. Looks like Franco times to me, the outfit. Yeah. 79. Okay, so now I come to today, And today, as the talk, I'm going to talk about these Yukawa hierarchies in F-theory gods. So first, I will give a short explanation of how you construct the models, how you compute the couplings. I will motivate the need for non-perturbative effects, and will show then how these non-perturbative effects induce couplings that one can compute and compare and discuss some properties. So, I mean, understanding the structure of masses and mixings in the standard model is an open, outstanding problem. So it's no surprise that Luis has addressed this problem several times. He has done some pioneer work, like pointing out how you can get a hierarchy in orbifold superstring compactifications already in '86. More recently, he showed how one computes systematically the couplings in D-brane models. More recently, he has been interested in the structure, Yukawa structure in F-theory models. And why F-theory? Well, one can use some, arrange some local configurations of branes to obtain realistic models. One can compute the couplings from overlap integrals, like in the heterotic string here, this is a picture of Luis. And also in type 2, one does integrals of 0 modes. But now the advantage is that these are localized, and then the computation is easier, and as I will show, it can be even reduced to some calculation of some residues. Also in F-theory, unlike in type 2b orientifolds, there are couplings like the 10-10-5 in SU5, which are already allowed at the perturbative level. So one can see F-theory as type 2b, but non-perturbative with a dilaton that is non-constant. In type 2b, the internal space is 6-dimensional, and there are 7 branes that wrap a surface, a 4-dimensional surface in the internal space. In F-theory, the internal space is 8-dimensional torus fibration, which means that at every point of this space here, there is a torus, and the fiber of the torus is the dilaton. The modulus of the fiber is the dilaton. But at the points where this torus degenerates, it's like here it's pinched, there will be 7 branes, but they also wrap the surface in the 6-dimensional space. So in both types of models, there are 7 branes that wrap the surface on the 6-dimensional internal space. And the theory here, on the observable theory in the space-time dimensions, will come from that compactifying the 8-dimensional theory. There is some group that in the F-theory models can be exceptional. Now, to obtain matter, there are other branes that will intersect here, and from the strings between the 2 branes, one gets this charged massless matter, which is localized on the intersection, and this intersection is a curve. So in a model, we have some branes that give the grand unified group. There are some other intersecting branes. There are these open strings in between, which are massless, and the intersection. Intersection is this curve, this line, green line. And usually at the intersection, the symmetry is enhanced, like from SU5 to SU6. And this is represented here more schematically, and you only see the edge of the surface. And, well, I put here the representation as well. There can be more complicated models with more intersecting branes. The model we want to consider is an SU5 model. There will be 3 of these curves where there is matter on 10 of SU5, on 5R of SU5, and the Higgs. There's a special point, the intersection point, and at that point, the SU5 enhances to SO12. So The effective theory in 4 dimensions comes from the theory in the 8 dimensions. The fields in 8 dimensions are just a scalar, which represents the degrees of freedom transfers to the branes, and some gauge fields. And there are the space-time dimensions, the internal dimensions, and we use some complex coordinates, U and V. The massless fields in 4 dimensions, as usual, are 0 modes of the fields in 8 dimensions. One does the usual expansions around 0 modes, substitutes in the action to obtain the 8-dimensional action to get the 4-dimensional action. And in particular, there is a superpotential that takes this form here. F is the gauge strength of the gauge field, and M star is the characteristic scale of the F theory. Is related to the string scale, as I'll show later. Now, this superpotential implies some F terms, equations of motion for the fields. There's also a D term, and this depends on the Kähler form of the surface, internal surface. But we will mostly be looking around the intersection point, and then this surface is just 2 copies of the complex plane, and this omega then is just the usual Kähler form of one complex plane and the other complex plane. So now, okay, so to solve the equation, we have to specify the background, and this will define the model. And in this SU5 model, we start with a background for the field phi, which is in the adjoint of SO12. It is proportional to the diagonal generators, to the commuting generators of SO12. So, and these are then some charges. It's holomorphic, depends on these functions U and V, so satisfies the equations of motion. And the important thing here is that it breaks SO12 to SU5. But also we see that if some of these terms are absent, then the symmetry is enhanced. Like if U is 0, this is not there, and then there is an enhancement to SU6, and so on. And the matter at each curve can be read from the composition of the adjoint of SO12 under this SU5. And then we'll see at this curve there will be 5R plus conjugate. At this curve there will be a 10 plus conjugate, and so on. Now, to get a chirality, one needs to add flux, and also to break to the standard model group. The flux is constant. I mean, these Q's are again proportional to this generator, some constants that will be quantized, as I will show. And the point is that the different fields here that will transform in this representation fill this flux in different ways, depending on the charges. And in particular, for the Higgs, the triplet part feels no flux, which means then that they will split from the doublets. And finally, we expand about these fluctuations for phi and for the gauge field, and the 0 modes are then will be the fluctuations. And we'll solve the F terms and the D terms, and indeed we find that there are fluctuations that are localized at these curves, which in here, I mean, here I'm represented as flat, and around the intersection, the curves are the lines. Yeah, U equals 0, V equals 0, and so on. And these are the fields that are localized. So to compute the couplings, we see first we start with the superpotential. We see there is, from here there is a cubic term for the fluctuations. You can write it very compactly with forms, but one can also expand everything and show that this is an overlap integral of the 0 modes. These A's are, by supersymmetry, they are partners of fermions. Now, one could substitute here and find these couplings, so substitutes the solutions of the equations of motion, finds the coupling, but there's another way shown by these people, which is simpler, as I will see, and this is computing the couplings via residues. And the main observation, which actually we made with Luis in a paper, is that the F terms are much easier to solve in a holomorphic gauge where the gauge field does not have these components. And in this gauge, the F terms will not depend at all on the gauge background, and one can solve them completely. For instance, fluctuations are the derivatives of some function, and this function is determined by the fluctuations of the other field. Here one finds complete solution, and there is some function which is holomorphic to solve the equations, and it's fixed by the condition that these C's are regular when this denominator is 0, but this denominator precisely defines the curves. And so these functions H are called the family or generation representatives. And so in this curve where the 5 is located, they will take this form. I goes from 1 to 3. This is the curve where the 10 is located. J goes from 1 to 3. In the Higgs, there is only 1, and this H is just a constant. So then to compute the couplings, we do the integral by parts and drop all boundary terms because the boundary is very far away, and very far away all fields have died down already. So in the end, one gets just a residue of a product of functions evaluated at this intersection point. And the functions that appear here depend only on these functions H. And one can find that these etas easily from the F terms. Now, if we substitute these explicit results, we find there is only one coupling for the third generation, and it's that one. But it's only one. So this is what's called a rank 1 problem because there's only one non-zero eigenvalue, and one would like 3 non-zero eigenvalues. There are some scales here that are related to the string scale, and later, if one wants to evaluate this the value, they find a value, when one will have to substitute then the scales. Now, to solve this, to overcome this rank 1 problem, one way is to include non-perturbative effects. And this is what Marchesano and Martucci did. They considered the effect of Gaugino condensation on distant branes wrapping another surface, not surface different from the one where the standard model, say, is located. And this is equivalent, the Gaugino condensation, to the D3 brane instanton wrapping this same non-perturbative surface. And the effects will generate a correction to the 3-level potential, the superpotential, which was this one. It's a sum of terms. There is a small parameter epsilon, which is related to the size of the volume of the surface here. And there are some functions theta that depend on this H, which is how the surface S and P is inside the 6-dimensional surface. So what one would like to do is to study the couplings from these non-perturbative corrections, which is a sum of terms like this. In a previous work, about a year and a half, 2 years ago, we studied a simple toy model with n equals 1. But now we have to go beyond. We have to do something else because the coupling that you get when n equals 1 will be proportional to the symmetric trace of 3 generators, and this is 0 for the SO12 and also for the exceptional groups. So in our case, this would give 0. So then we decide we go to n equals 2, and indeed we found some couplings, but still there was only one non-zero eigenvalue. If we go to greater values of n, this doesn't solve the problem. So here, I think it was mostly Luis and Fernando. They got the idea, why don't we consider n equals 0, which looked trivial initially. But no, because if theta 0 is non-constant, then this really will give corrections. And when for theta 0 to be non-constant, you look at the formula, and you see what you need. What you need to get these functions to be non-constant. And yes, according to the definition of what appears here, what you need is that the non-perturbative surface, which is now this violet thing here, will intersect the surface S, but not directly the surface where the standard model is. But the other surface, the green surface S, has to intersect the surface with the standard model is. If this is the case, then this theta 0 will not be the constant. And this is exactly what happens in the type 2b description of the model. So this, we argued that this theta 0 can be non-constant, and look at the couplings induced by theta 0. And this, that means we start with the superpotential and try to compute the couplings. And this is, again, more easily done by residues. I say here holomorphic couplings because these are the couplings purely due to the superpotential. So we solve the F terms. The residue formula will not change because here there are no new cubic terms. So it's the same residue formula as before, but what changes are the functions that appear here. And this is something one can easily get from the F term. So we have all the ingredients, substitute, find the couplings. And there are some new 3 couplings that are induced, taking this theta 0 to depend linearly on the coordinates. For theta 2, the complication is more complicated because one has to correct the background after because of the epsilon effects. And they're really messy, horrible. But then one can they simplify implementing this generalized Cyber-Witten map to transform to some hat variables. In these hat variables, one can again go to the holomorphic gauge, and then the F terms are simple. One can solve them. The residue formula now has epsilon corrections because here there will be cubic terms, but these epsilon corrections are again proportional to the coupling constant due to some special properties of traces in SO12. And well, one computes and gets 2 different couplings. Now, up to now, I have talked about holomorphic couplings without taking into account the kinetic terms, the normalization of the wave functions. Now, to take that into account, we just multiply the holomorphic couplings by some normalization factors. And these normalization factors, for instance, they are inverse of norms. And these norms, now, they do depend on the fluxes. So these physical couplings depend on the fluxes. Okay. And this is important, for instance, to get that the couplings for the down type quarks and the leptons are different because the hypercharges will be different. And the matrix we get has this structure here. I have normalized by this coupling. You see there is, the hierarchy of eigenvalues. There's 1, there's the next, there's order epsilon. The third eigenvalue will be order epsilon squared, but we cannot compute it reliable only having these two order epsilon. But still we see this hierarchy between first, second, and third generation. And if we look at in more detail, then we can compare with data. You have to run the data to the unification scale, and for that we use this analysis of Ross and Serna. And some features, third generation Yukawas are large. I can explain this in more detail how we get it, but since I'm getting ready. Also, the reproduce the hierarchy between second and third generation for the masses, and we can even reproduce this ratio. So final comments. We've seen that these non-perturbative effects to induce a superpotential, and there are some corrections to Yukawas that one can compute using residues, for instance, and implementing this cyber-within map. In this SU5 model, we computed these couplings and showed that indeed we can get a matrix of rank 3. If we include the flux-dependent normalization, then we solve this. We can get different couplings for the down-type quarks and leptons. We reproduce also the hierarchy between second and third generation. In progress, with Fernando, Diego, and Gianluca Soccarato, who is here, we are trying to compute couplings for the op type quarks in a model where the group at the unification is 6. Something one perhaps can look into is whether there is a non-commutative formulation for these non-perturbative effects, even for the other values of theta. For theta 1, we showed it in the previous work, that these two were equivalent. So maybe they are equivalent for other values. So now I come to tomorrow. And for tomorrow, well, I wish I knew. All I can do, best I can do, is again borrow some words from Alfonso. And maybe Luis will say some of these things too, especially read all books for sure. He will tell you you have to do that. Have all friends. Here are some old friends. Some of them are here. Some of them I don't know. But I see Maria Jose, for instance. Here's Maria Jose. Alberto, Mariano, Belén. This is Valle, no? And Branco, Espinosa, Fabio. Well, those are the people I don't know. I don't know when this was. Guido is there, yes, Guido is. Fabio Svirne is here, yeah. Fabio is the one that, yeah, even at that time didn't have much hair. And of course, Gustavo and Guido. I mean, Guido is the quintessential. Here's another picture. Okay, you see that really Luis really plays guitar. This was called a Super Carmen in '84. It was one of these CERN plays, the Christmas plays. You know? And I see, well, this is Alvaro, of course. And of course, he would be the torero. He would not be Don Jose, never. Okay. And finally, some friends of a different species also. And the cake to end. So, Luis, I wish you many more happy, healthy, and productive years to come. And, well, lots of thanks for friendship, enlightening collaboration, and support through my career.
Thank you very much. Questions, please?
The secretaries from CERN send their regards. Yes. Oh.
Why 10 to the 31?
Because of the 31 papers.
Maybe I have a question. What about this dependence on thetas on the coordinates u and v? What is known about this?
I mean, we know it's a function. So we just take the simplest function, a linear function.
Okay.
That's
and
for the other,
okay.
Yeah, we just expand around the point of intersection. And that's all.
Other questions? If not, let's thank Anne-Marie again.
Okay.